section 3.1 deals with critical numbers and absolute extrema on an interval. When we're talking about extrema, we're talking about maximum points and minimum points, but we're not always talking about the absolute max or the absolute min. Okay, we're not talking about it all the time over the entire graph, but maybe over a certain portion of the graph. So we may limit it to a certain interval. There are two types of extrema. There are relative extrema on an open interval. We're not going to deal with that today. And then there are absolute extrema on a closed interval. That's what we're going to talk about in this section, or the absolute extrema. But most of chapter 3 is going to deal with relative extrema. So this is sort of a little standalone section, but it is a good precursor and introduction to certain things that you need to know for the rest of this. So we'll spend most of our time in this chapter on relative extrema, but for this one section we're going to talk about absolute extrema. The first thing you need to understand is that to find extrema of any type, whether it's relative or absolute, we first have to be able to find all critical numbers. So here's what a critical number is. They are the x values of a function where the first derivative is either 0 or undefined. So in all the places where you'll have a horizontal tangent, a vertical tangent, or a non-unique tangent line, basically. To find the critical numbers, you just take the derivative and set both the top and bottom equal to 0 and solve it. What you have to make sure you understand is that in order to do that, you must have a least common denominator. That's why we have tortured you so much by making you get common denominators. You have to have them in order to take a single numerator and a single denominator and set them equal to 0. Also, because you're going to be solving for those, it'll be really important that you factor them. So that's the reason that we've put all of that algebra upon you. You know, they need to be in factored form with the least common denominator. It's also important to note that there's a critical number at any sharp turn in a graph, such as the vertex of an absolute value function. So if you're dealing with absolute value, you need to take that into consideration as well, wherever the vertex is there, where the absolute value actually goes to 0. Technically, that is because the derivative does not exist there, since the derivative from the left and from the right are different, but they do show up as important numbers, and we include them in the critical numbers. So if we come across an absolute value, we'll have to handle those a little bit differently. So the first thing we want to do is just practice finding the critical numbers. We're not going to do anything with them. We're just going to practice finding them so that you understand how to get them. Later we'll figure out what to do with them. So the first example is find all critical numbers of g of x equals x squared times x squared minus 4. To find critical numbers, you have to take the derivative. In this particular case, I think it would be easier to distribute rather than use the product rule. Is that okay with you guys? Okay, so let's distribute first. And we have x to the 4th minus 4x squared. Then we'll take the derivative. We have g prime of x is equal to 4x cubed minus 8x. So that's our first derivative. And to find the critical numbers, all you do is make sure that you have a least common denominator, if there are any denominators, and then you just set the top and bottom equal to 0 and solve it. So, since there are no denominators, we're just going to set the top equal to 0, and we can factor out a 4 and an x. And that will leave us with x squared minus 2. Okay. And since we're setting it equal to 0, we'll just set 4x equal to 0, and x squared minus 2 equal to 0, and we'll solve them both. So we get x equals 0, and x squared equals 2. So we get x equals plus or minus the square root of 2. So it looks like that function has 3 critical numbers. 0, positive square root of 2, and negative square root of 2. So we'll learn later that if there are turning points on a graph, they're going to occur at those numbers. For our second example, we're going to find all critical numbers of the function h of x equals 5 over 2x minus 3 quantity squared. Because the top is just a constant, we can work this problem without using the quotient rule. So I'm going to rewrite it as 5 times 2x minus 3 to the negative 2 power and take the derivative from there. That would be power times coefficient, down 1 on the power, times the derivative of the inside. And if I clean that up algebraically, I get negative 20 over 2x minus 3 to the positive 3 power. So there's my derivative. In order to find the critical numbers, you simply take the top and bottom and set it equal to 0. Now the top doesn't produce any, so we have no solution here, so we don't get any critical numbers from the numerator. That also means that there are no horizontal tangent lines, so there are probably no turning points, because like a vertex or anything like that. So that would be a horizontal tangent line. For example, like in this graph, there are 2 horizontal tangent lines. But obviously this graph doesn't have any because the numerator didn't produce any critical numbers. So if it doesn't have any there, it can't produce those. So we'll learn all about that a little later. How about the denominator? How do we solve it equal to 0? What do you do first? Take the cube root of both sides. And that will produce 2x minus 3 equals 0, 2x equals 3, and x equals 3 halves. So this function only has one critical number, and it's occurring at 3 halves.